Hello, welcome to my application number 6 that is going to be talking about correlation. For this problem, we're going to be determining the correlation between white platelets and the age of patients. And we're going to be doing that using a 95% confidence, which means we want to be 95% confident about the answers that we're going to give, which is actually pretty good confidence. And then after we do all of that for this big problem, we're going to actually do the same thing and take a look at white platelets and red blood cell count, and then the waist of a patient and their weight. So we're going to determine the correlation between each two things. Now, to actually determine that correlation, this is what our to-do list is actually going to be. First is to choose which will be our X variable and our Y variable. So will our white platelets or age be X or Y, is what I'm saying. Then second is we're going to determine our Pearson correlation coefficient. Third, talk about the significant linear correlation. And then fourth, is there a correlation? And finally, fifth is we're going to determine the same for our other two problems that I just mentioned. Now, to find Pearson's correlation coefficient, we actually had the assistance of Excel, because Excel actually had all of our data points already inputted for us, so it was very useful to use. And also, correlation coefficient, to find it, the formula is crazy hard, so we're just going to use Excel. What you do is you'll just type in equal sign, and then CORREL. And then I actually, just to go ahead and stay consistent on which variable is my X and which variable is my Y, I put my Y variable first, which is my white platelets, and then I put my age, which is my X variable. And then that actually came out to a correlation coefficient number of negative 0.07. Now there's three ways to actually take a look at the significant linear correlation, which is to look at the graph. We'll actually be able to look at in just a second. We're going to take a look at the Pearson correlation table, as well as do hypothesis testing. So first, we're going to actually take all of those data points that we had in our Excel, and we're going to graph them. And on our x-axis, which will also match our x variable, is the age of our patients. And on the y-axis will be our y variable, which is the white platelets. And as you can see, the title, of course, is going to be the impact of age on white blood cell count. And that's a sample size of 300. Now, a main way to actually just use the graph to determine correlation is to see if there's a negative slope, a downward slope. Is there some kind of similarity of a line being present? So if we take our little laser point here, can we match all of our data points on a line following that? And that would be a positive slope. And no, they're not really matching that well there. Let's try a negative slope. So we're going to go the opposite way and going down. They're still not following. They're kind of staying in this grouped area here. They're staying in this grouped area right here. So that using the graph, we can kind of determine that there might not be a correlation between age of our patient and their white platelet count. Now, if we actually use the Pearson correlation table, which is easily being able to find on Google or any image searching really, so you'll see on this side right here is going to be our DF equals n minus 2. So degrees of freedom equals our sample size minus 2. So like I previously said, our sample size is 300. And minus 2 would be 298 through some quick simple math. And as you can see, our highest number present is 100. But right below it is the infinity sign. Now I'm going to take you back to our correlation coefficient number, which was negative 0.07, which if it was related, it would be a negative slope. So we'll need negative 0.07 for it to negative 0.07 to be on our table here to determine whether or not that it will be related, correlated, maybe. So if you see here, we're going to go to our 95% significance of a two-tailed test because this is correlation. And then 0.087 is actually the number that we would need on our correlation coefficient for them to be somewhat related. And going back, we have negative 0.07, or just take it the negative way, 0.07, which is not this number. It's less than the Pearson correlation table. So the graph told us that they're not related, correlated, and now the Pearson correlation table is telling us that they're not correlated. Lastly, we're going to do hypothesis testing, which means we're going to need a testing statistic, and we're going to use, again, technology in here, but this time Desmos, which is an online graphing calculator that is really awesome to use. So as you can see, we're going to decode our testing statistic and find out which every variable and what symbol each means what. So our XY is actually our Pearson correlation coefficient number, so that negative 0.07. So if you can see on Desmos, we have negative 0.07 as that replacement number, times the square root of n minus 2. So times the square root of our sample size, which is 300, minus 2. And as you can see on the right side, I also replace those. And that's all going to be divided by the square root of 1 minus the Pearson correlation coefficient to the second power. So if you can see, we did 1 minus negative 0.07 raised to the second power. And we did all of that, and that equals negative 1.20543764,187. So a really long number. And that number is actually going to be our t-score. So that's very important. It's not a z-score. We're not going to use a normal distribution table to determine. We're going to use a t-score, which means a t-distribution. To determine for our t-distribution, I also referred back to Desmos with this help. So using Desmos, we put in the formula t-dist and parentheses. Now, this is where the 298 is actually our degrees of freedom. And since this is a correlation, we'll do 300 minus 2 to be our degrees of freedom, which equals 298. Now, there's two ways we can determine the two-tailed test that we're going to need for the t-distribution. The first way is 2 times the t-score, or the second way is 2 times 1 minus the t-score. The difference between those two is you want to multiply the 2 by the lesser number. So if the t-score itself is smaller, or 1 minus t-score is smaller. And for this case, the actual t-score itself is smaller. So if you can see to the right, I took that p-value of 0.11495350204, and I multiplied that by 2. And then that ends us with 0.2289907000408. Really, really big number. Now we're going to talk about our final conclusions. We're not only going to talk about our white platelet and age, but we're also going to talk about our 2 other problems. So first, tackling our white platelet and age. Because our p-value, and we had to multiply that, it actually was failed evidence to show correlation between age of a patient and their white platelet count. So all we can actually say about those specific categories is that the average age is 47.04 years old of a patient, and their average white platelet count is 6.5 per microliter. But we're going to actually go ahead and look at the other two examples. First being the white platelet count and red blood cell count. So we actually took the p-value and we also looked at the graph, and we also looked at Pearson's correlation table, just like we did previously. And we were able to have enough evidence to actually show correlation between the white platelet count and the red blood cell count. Because there's enough evidence, we can actually say as red blood cells count goes up, so does the white platelet. And similar is for waist and weight. Because 0 is definitely less than alpha, our confidence level, we are able to say that as weight goes up, so does size of waist. So this actually is a great example of one showing no correlation, and then others showing great correlation or strong correlation.